Okay, so we will start discussing the simple harmonic oscillator. Simple harmonic oscillator. Well, it is sometimes one wonders why when there is a need for resorting to an example, specific example, we always go to either simple harmonic oscillator or harmonic oscillator in general. Simple is really simple to handle. To illustrate the general theorems that we develop in the context of quantum mechanics. Well, another beautiful example and a simple example is the naive hydrogen atom. That is the quantum mechanical Coulomb problem. Because these are exactly solvable, so you can really illustrate all the theorems and all the new ideas you develop in this context by solving this problem. That's one thing. This practical usability as a simple example. And the second example is most of the interactions that we come across to at the sort of approximate scale are all of this type. That is, this harmonic oscillator type of interactions that dominate many problems in the solid state physics and in the other fields of physics. Sometimes you want to really mimic the interaction between different type of entities in certain problems. As a model, you resort to this, and it's a very good approximation. What do I mean? If you have a sort of an arbitrary interaction represented by an arbitrary function, if you really expand those functions into Taylor series expansions, if you retain only as a perturbation argument, those few terms in the expansion, you have a constant and linear term and a square term. And if there is certain symmetry which sort of rules out the linear terms, you can really approximate any kind of ordinary non-singular interaction in the form of a harmonic oscillator. So in that sense also it is very useful. Therefore, we have to have a good understanding of simple harmonic oscillator in the context of quantum mechanics. So let's start discussing it, and we'll use the so-called operator method. It is also consistent with the previous discussion that we have presented in relation with harmonic oscillator, namely the solution of harmonic oscillator in the Heisenberg picture. Remember, we have been able to solve Heisenberg equations of motions and obtain the time dependence of the x and p operators in terms of their initial values, which are the so-called Schrödinger operators, because Heisenberg picture and Schrödinger operators coincide at t equals 0 or at the origin of time. We usually choose it to be the t equals 0. Therefore, we have that information in hand already, so we have a sort of some kind of understanding on what the harmonic oscillator solutions look alike. And remember, at that level, we have seen that x of t and p of t came out to be an oscillating function, operator function, of course, of time. It has terms in it like cosine omega t, sine omega t, and times x at 0, p at 0. So you say that, that's nice. The operators also oscillate as a function of time, as in the classical case. Because if you solve Newton's equation of motion or Lagrange equation of motion for the harmonic oscillator, you get oscillating functions. It's a function of cosine omega t or sine omega t. Same happened at the operator level. That's x of t and p of t. But life is not that simple. We'll see that whatever happens at the operator level, whether we can carry it over to the classical regime by considering the expectation value. Because remember, the correspondence principle tells you that the operators in quantum mechanics and their expectation value, when you consider their expectation value in given states, those things are the ones which correspond to the classical quantities. So having an oscillatory behavior for the x and p operators is something, and considering their expectation values is another thing. And if you want to have a correspondence relationship between quantum and classical, that is what we have to do. But that's going to come next as we proceed. So the motivation is twofold. One is they are beautiful, simple examples. Second, well, there is so much in nature which is of that type, interactions in many fields of physics, not only in this context, but in many other things. So remember, let's start by reminding ourselves the form of the Hamiltonian. Well, this expression is, of course, the same in classical and quantum. They are in one dimension. That's why we call the simple harmonic oscillator. And if we need to distinguish between classical and quantum, then I will use the capital letters for the quantum operators. But at this level, as there is no danger of confusion, I will continue using the simple, beautiful letters, little x and little p. It means in the quantum mechanics, these are operators. They are numbers in classical physics, but they are operators in quantum theory. This operator technique, okay, we'll use the operator methods. This also is due to this great physicist Dirac, this particular method. It is based on the following really simple observation. That's a nice mathematical trick. Let's try to write this in this following form. 1 over 2 m omega squared, x squared plus p squared, m squared, omega squared, correct? Omegas cancel, there is 1/2, m's cancel, so indeed, that's a nice way of writing the expression. It's aesthetically nice. Then from that point on, you do the following. If we were in classical physics, and in classical physics, there is no ordering problem, right? It's a problem of quantum mechanics, that you have to watch the orders. If we were in classical, I could write a nice factorization. You may wonder sometimes when people write things, whether they come out of the head. No, it's based on some simple observation and instinct, and the instinct is mostly classical. So if we were classical, I could have factorized that. How do I do that? I write it as 1/2 m omega squared, then x plus I p m omega, and x minus I p m omega. Correct? A plus IB times A minus IB, and when you really write them, you get A squared plus B squared, thanks to these I's, the famous I's. Well, that's classical. Nice, but that classical thing will give us sufficient inspiration. If I write the factor in the front, in the following form, this factor in the front, I take it up because I want it to be visible, and I will write it in the following form. M omega over 2h bar square root square. Well, you may say, oh, that's really circular. No, it's not circular. Well, there is a meaning associated with the m omega over 2h bar. And then, this m over 2h bar, this is 1/2 m omega squared. To compensate it, I multiply this with h bar omega. Indeed, correct, right? H bars cancel. 1/2 m omega squared, then it reproduces this one. So this is really how it is moving. Once that is done, then you can split one part of this square root in front of this and the other in front of that. It gives you, we are still in classical, mind you, that's a very important thing. It enables you to write the following definition, to introduce the following definitions. You will see the advantage of those definitions. 2h bar, x plus I p m omega, and of course the dagger of this simply is the minus sign in here. Everything is the same. First of all, there are several observations one can come up with that these are not Hermitian. Now, you see, I move to quantum mechanics. I say, I make these identifications. So these are definitions. def, and def. And we have moved to quantum mechanics, and we have made the following definition in terms of the x and p operators and those constants. So A and A dagger are not, because A dagger is not equal to itself, A dagger is not equal to itself. Is this a problem? Well, those of you who are really brainwashed by the motto that observables are Hermitian things and only they are the ones which have the eigenvalues which are real, etc., etc. So this is not an observable. You may say, so what? We have observables x and p, and these A and A dagger are the things, sort of intermediary things defined in terms of the x and p. There's no problem. Being non-Hermitian for these A and A dagger are no problem because they are not observables anyway. They are defined in terms of these observables. So these are now in the quantum mechanics operators, and temporarily let's put OP and OP to emphasize that we move to quantum mechanics and we are really working in terms of the operators. Then some of you will say, go back to this and check this. Is this valid? Of course, not. So what we do then is, in order to correct and obtain the correct form of this factorization is a classical one. Whether it survives in quantum mechanics or not is another thing that you have to check. What do we do to check this? To correct the expression, consider the following product. Well, you already felt what kind of gimmick we are using. We go in that factorization at the classical level enabled us to identify the new operator A and A in the dagger, and I could consider the product now at the quantum mechanical level and see what the extra term which will survive. I will add it to the expression and we'll get the right expression then only. So what is the A dagger and A? I take these and multiply, so m omega divided by 2h bar, the square roots, and this the minus 1 first, because I take the A dagger. So it is this. Let me write it. Let's not be very stingy in using time. So it is this expression, right? Which is x squared plus p squared divided by m squared omega squared from the first to first, second to second. But notice that there are cross terms, which were not there in the classical physics because of the commuting of the operators, but here there is cross terms, which is I 1 over m omega xp minus px. Commutator. That's it. That's the quantum mechanics. You started from classical, I made the identifications and go back to quantum mechanics, and you see what the new things are. IH bar. If it is IH bar, I and I is minus, this thing is minus H bar m omega. And therefore, this entire thing is m omega 2h bar times x squared plus p squared divided m squared m omega squared minus 1/2, right? M omega h bar and h bar m omega 1/2. What is this expression now? If you just enter this in, this is this first term is, notice that it is h bar over m omega, h over m omega, right? If you compare the expression for the h, this h is, the simplest thing is compare the p squared term. There, the coefficient of p squared is 1 over 2 m omega. Here, 2m. The 2m is here. There is an extra h bar omega, right? So you divide it by that. Omega, one of them is cancelled, and this survives, and so I put it in here. So what do I get then at the end of the day? H is h bar omega, sorry. H is then, this moves to the left, A dagger A plus 1/2 times h bar omega. Okay. This is the new form of the Hamiltonian written in terms of the A and A dagger operators. Nice. Well, this particular form is quite nice. Historically, when Mr. Planck was trying to understand the black body radiation and that black body radiation spectrum, that is intensity as a function of the temperature or the frequency of the light, in order to explain that Gaussian type of profile, he had to introduce a set of discrete energy levels associated with he thought of, wrongly, he thought that walls are the metallic walls, heated metallic walls are composed of oscillators. And oscillators have discrete energy levels, he imagined. Well, nowadays in the modern terminology, we think that it's not the walls, it is the field itself, electromagnetic field, which are composed of infinitely many oscillators. Well, it's really these set of A and A dagger operators when you quantize the electromagnetic theory, and Mr. Glauber has eventually used it very successfully in formulating a quantum optics, and he received Nobel Prize for that. So when you see these A dagger A and this form, it is not, you shouldn't really think of it in terms of that the simplest problem of quantum mechanics. It has really very broad dimensions. It's beautiful when you come to think of it. Okay. So what next? The next step is to pursue the problem in terms of these now A and A dagger operators. Let me proceed along the lines that I have introduced. Now let's give this a name, define. Well, let me use definition. I will call this operator A dagger A. Notice that H is simply a factor times this n operator, right? So H is H power omega n plus a half. Nice. What does it mean? When you have an expression of that sort, you have two operators. One is the capital N, the other is the Hamiltonian, and obviously they commute because it is just a constant times the other one. So they commute. Well, till now we have developed a beautiful structure of quantum theory. When you have two commuting operators, they will have common set of eigenvectors. Or in other words, if you use more sophisticated terminology, you can diagonalize them together, etc. So they have a common set of eigenvectors. Okay. So once we made that really simple observation, we can start constructing that eigenvalue problem. Let me introduce the eigenvalue problem in this fashion. Remember our previous custom that we use the capital letter for operators and little small letters for the eigenvalues and eigenvectors of the same operator. So that defines for you what an eigenvalue problem. Well, you may say, what is the meaning of those eigenvalues? For instance, do I know at this level whether the n's are numbers, any numbers, rational numbers, or integers, positive integers or not? Well, I don't know yet. The next step is to demonstrate all those features. We will demonstrate that these n's will be, okay, let me give the answer. We'll show later, this is important because that's a promise which we postpone, the proof which we postpone for a few minutes later. We will show that n are positive integers. As I said, this is a claim to be proven. I'm just reminding you which way we are moving, otherwise it's not a proof. But we know one thing, right? That n's are real. You may say, why? Well, because n is Hermitian. Let's demonstrate that n is Hermitian. Although A and A dagger are non-Hermitian, n is beautifully Hermitian because you just take the Hermitian conjugate of this thing. Hermitian conjugation requires that you reverse the order and take the Hermitian conjugate of the second one first and the first one next, dagger of the dagger is itself, so it is really Hermitian, there is no problem. N is a good operator which is suitable to the quantum theory, so n's are real numbers. As a consequence of this being Hermitian, n's are real. At least that much is guaranteed. But what is the nature of these real quantities? We'll demonstrate that those real quantities are positive integers. Well, that will come next. The first thing that we have to trivially illustrate that as these are commuting, and then we said they should have common eigenvectors, and the eigenvalues associated with that common eigenvectors for the first operator is n. What about the other h? So to understand what are the corresponding eigenvalues for the h in the same eigenvector basis, we take the h and act on the n, which is h bar omega n plus a half, right, times n. This gives you the n. Therefore, this n plus a half times n is these are the energy eigenvalues. Common set of eigenvectors. One set of eigenvalues are n, the other set of eigenvalues are n. Eigenvectors are the same, common, but eigenvalues are different, of course. And n's are real numbers, en's are also real numbers. Involves little n times h bar omega. Omega is the number related to the spring constant of the harmonic oscillator, right? That we know. Now we will set ourselves with the task of demonstrating this important fact that n's are positive integers. We'll show later that, and we said n are positive integers. Let's demonstrate that. To prepare ourselves towards that direction, we have to do some preparation for that ultimate purpose. So that requires that we have to reveal most of the properties of the A and A dagger that we have introduced. So let's try to construct them. Properties of A and A dagger. This set, okay. Let's work out the commutators of these operators with the capital N. For instance, this one, N and A, is what? This is A dagger A and, I forgot to, of course, work out the commutator of A and A dagger first. Let me do that, sorry. The first one is A and A dagger. What is that commutator? Well, if you remember the definition of the A dagger and A with those factors, let me put the factors in the front. M omega over 2h bar times x plus I p over m omega, x minus I p m omega. X with x is 0, p with p is 0, x with p minus I over m omega, x with p, and plus I, so it is twice. The other cross term. First with second, second with first gives you a factor of twice. So this one is IH bar. I give you the positive sign, so it is 2h bar m omega. This entire thing, which is exactly equal to the opposite of that factor. So this commutator is 1. That's very nice. A with a dagger is 1, and that follows from the commutation relations of x with p. So if I now use that, the commutation of n with a is trivially computed because a commutes, so it is a dagger and a second factor to the right. This is -1, so it is minus a. Similarly, if I compute now n with a dagger, and this is a dagger a to the right gives you 0, this to the left, a dagger, a and a dagger, this one is 1, so it is a dagger. So these are important quantum commutators. N with a gives you minus a, n with a dagger gives you plus a dagger. So it eventually will be very useful for the ultimate demonstration that a and a dagger are ladder operators in the n spectrum. It is these commutation relations which will lead us to that result. Let's start considering the following. If I now consider this particular state, question, of course, the trivial question, is n an eigenstate of the a and a dagger operator as well? We don't know, and probably not. Well, we know that n's are common eigenvectors of only these two operators. In order to be a common eigenvector of those a and a dagger, also they should be included in this commuting set of operators. That is, a should commute with the h, a dagger should commute with the h, and similarly with the n. Of course, we have demonstrated that n doesn't commute with a and a dagger, so they are not eigenvectors. N are not eigenvectors. You may say this is too trivial a statement, but mostly those simple statements are important. So these are not eigenvectors of a and a dagger because these two do not commute with the capital N. If they are not eigenvectors, how do they act on the n's? That is the question. In order to now find the action of a dagger on n, I consider this new state something. It is another state. A dagger acts n and moves it to another state. Whether it stays in the spectrum of n is something else, but it's not the same as before. To understand what this is, I act on it by the capital N now. Then, here, I have to look at that n a dagger. What is it? N a dagger is a dagger n plus a dagger. I just read from that commutator. That's the reason why I worked them out first. And then n acts on n, gives you the little n, and that's a number. Then you take that n plus 1 out, and you get a dagger n. Aha. That's really a beautiful result, isn't it? Through this action, I have discovered that this new transformed state is an eigenstate of the capital N with the eigenvalue n plus 1. So the lesson which we extract from here is that a dagger n is a state proportional up to a constant, normalization constant, to the n plus 1. Because that shows that it should be an eigenvalue with the n plus 1. Reading from the eigenvalue equation, this is proportionality sign, that this must be proportional to n plus 1. And how do I write it as an equality? Well, if I start with the normalized eigenvectors, I have to ensure that we introduce a normalization constant. So if we forgot to introduce in here the following, n's are introduced as normalized eigenvectors. Right? You introduce that normalization by hand from the beginning. That's an important fact. So, but you don't know whether the action of a dagger on n preserves the normalization. It doesn't. Because in order to preserve the normalization, it must be a unitary operator. It's not a unitary operator. It's not even Hermitian. Therefore, if this is originally normalized, you act on it by that. It doesn't stay normalized. So it's only proportional to this state. In order to write inequality, I put a constant, C plus, for instance. Fine. Let's repeat the same exercise for the A. So it tells us, the first thing this tells us is that when a dagger acts on n, it increases the number n by 1 unit, up, whichever. What about the A? In order to understand the role of A on n, I repeat the same method. I act on it by the capital N, and look at the first commutation. NA is AN minus A, if I read it from here. Then this N, when it's acting on it, gives you a number N. Then numbers commute with the operators. You take that number out. What is left over is this. Which means that this state is an eigenstate of the n with the eigenvalue n minus 1. So the action of A on n was to decrease the number n by 1 unit, to lower it. So an should be proportional to n minus 1. I'm not going to repeat the argument. We have talked about it in length. So all these things are to be decided by the requirement of normalization, right? Okay. Now let's try to determine those constants. So I write a dagger n is C plus n plus. Now I can write it as an equality. I put the constant in, therefore if it has lost its original normalization, this is to compensate against that loss of normalization. How do I determine the C plus? I just consider the inner product of this with itself, that is, I project this on NA. If you go from this equation to its dual space counterpart, the ket went to the bra, the operator went to its Hermitian conjugate, so that's A. Numbers go to their complex conjugates, therefore this is the mod square n plus 1 and n plus 1. What is A dagger? A dagger you read from this commutator. A dagger is A dagger A plus 1. A dagger A is n. So it is n plus the identity operator. Sandwich between n plus identity. That's the left-hand side. And right-hand side is C plus mod squared. Normalized, so it is 1, this one. So what is this? The left-hand side. N Hermitian x to the left gives you little n, and then nn is normalized. So what you get in there is n plus 1 in the left-hand side, and C plus mod squared is in the right-hand side. So C plus mod is the square root of n. C plus up to a phase is n plus 1. E to the I alpha. In principle, you have a phase, right? Because it is the complex number in general, and the mod of the complex number is determined by this argument. The phase is totally free. We are in no position to determine the phase. We usually take the phases to be 0 because in physics, except in very special cases of discrete symmetries, the phases do not play an important role, and so we set them equal to 0. Set equal to alpha is set equal to 0, so it is n plus 1. Let me repeat the same analysis here for the other one. Here. A on n is c minus n minus 1, because we have demonstrated that it decreases the number n by 1 unit. We have introduced a constant to compensate against the loss of normalization, and we take its inner product with itself. That is, we again project this on n a dagger. That is, take it to the dual space with the rules that we have derived. So we have in the left-hand side n, a dagger a, n in the right-hand side, the c minus conjugate, and it's normalized, so it is c minus mod squared. This is n, therefore n acting on the n eigenvectors little n, so you get c minus mod squared is n. Therefore, you move it to here, take the square root and set the phase equal to 0. So I can finally write those results down, and these are beautiful, important results. A dagger n is n plus 1 times n plus 1. A n is n times n minus 1. Nice results. That shows that they are indeed the ladder, and how they change the values of the n by acting on them. So it is a very good point to stop, to give a break before proceeding.